Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 10th graders 2024, problem number 3. Let a, b and c be non-zero complex numbers such that the modulus of a equals the modulus of b equals the modulus of c, and a plus b plus c is a real number and abc is also a real number. We wish to prove that a to the power of n plus b to the power of n plus c to the power of n is also a real number for all non-negative integers n. It's a rather standard problem, but you have to know how to solve it, so here are my hints. Well, the key is to observe that 1 over z is the conjugate of z over the modulus of z squared, where z is non-zero complex number. Show that bc plus ca plus ab is also a real number. And notice that if we denote the elementary symmetric polynomials, sigma 1 as a plus b plus c, sigma 2 as bc plus ca plus ab, and sigma 3 as abc, and let p of n be a to the power of n plus b to the power of n plus c to the power of n, then Girard-Newton formulae say that we have this type of recursion. It's a well-known identity, also known as Newton's identity. Pn plus 3 equals sigma 1 Pn plus 2 minus sigma 2 Pn plus 1 plus sigma 3 times Pn, where n is any non-zero, any non-negative integer, any natural number. And use this recursion to prove by induction that our theorem is true. So give this problem a try. Alright, so let's notice the following. Let's investigate 1 over a plus 1 over b plus 1 over c. Well, this makes sense because a, b, c are supposed to be non-zero. Alright, what is 1 over a? 1 over a is this conjugate of a over the modulus of a squared plus b bar modulus of b squared plus c bar modulus of c squared. Alright, now, by our assumption that moduli are equal, we can write it as a bar, b bar, c bar over modulus of a squared. Now, the conjugate of a plus conjugate of b plus the conjugate of c is a plus b plus c conjugate over modulus of a squared. And now notice that by assumption a plus b plus c is a real number, so there is no need to place this conjugate. And of course, this again is a real number. Alright, this is a real number. So let's take this quantity and let's multiply by abc. Because notice that bc plus ca plus ab can be written as abc 1 over a plus 1 over b plus 1 over c. We have demonstrated that, well, abc is a real number by assumption, and this 1 over b, 1 plus 1 over b, 1 over a, 1 over c is also a real number. Product of two real numbers is again a real number. Alright, so now let sigma 1 be a plus b plus c, sigma 2 be equal bc plus ca plus ab, and let sigma 3 be equal abc, and let p of n be equal a to the power of n plus b to the power of n plus c to the power of n, for any natural number n from 0. We will prove by induction that Pn is a real number. We will prove by induction that for any real number, for any non-negative integer n, Pn is a real number. Alright, so let's start. What is P0 proof? P0. Well, P0 is a to the power of 0, b to the power of 0, c to the power of 0 is 3. Obviously a real number. What is P1? P1 is a plus b plus c. It's exactly the same as sigma 1. And sigma 1 is a real number by assumption. Alright, what about P2? P2 is a squared plus b squared plus c squared, and this can be written in this nice way. It's a plus b plus c squared minus 2 bc ca ab, which is sigma 1 squared minus 2 sigma 2. This is real, this is also real, so we have a real number once again. Now, an inductive step. Let's suppose that Pn plus 1 and Pn plus 2 are all real numbers for some natural number n. Now it's time to use Girard-Newton formula. Girard-Newton formula say that Pn plus 3 can be written as sigma 1 Pn plus 2 minus sigma 2 Pn plus 1 plus sigma 3 Pn. It's a well-known formula. You can look it up on Wikipedia, for example. I will not prove it, because proof might be quite lengthy, and I wish to keep this video quite short. Now, notice that since this is the case, this is also a real number, because everything which appears right here is either real number by assumption or by inductive assumption, which concludes our proof, really, because this closes induction and this closes our proof. So the basic idea was to express our an, bn, and cn in terms of these basic elementary symmetric polynomials, and that was it. So thank you very much for watching, and I will see you next time. Goodbye.